Hello, welcome to the course Excelling with Mathematical Modeling. Today we will be discussing about the drug distribution inside our body, that kind of model we will be discussing. So, to start with, this whole process, that is the study of the movement of drugs in the body, is called pharmacokinetics. So, in this pharmacokinetics, people use these mathematical equations and utilize them to describe the movement of the drugs through the body. So, how we model that? So, before going into the model, let us see that how actually this drug works. So, if you see that once this drug enters inside your body, it dissolves and it passes through certain membranes, or sometimes especially the stomach, or otherwise if it does not dissolve, it go directly to the intestine. So, in the intestine actually they start this dissolving, they pass through the intestinal wall and then ultimately they come to this liver, and from there the drugs are distributed. And if it is some sort of through the veins, then you can see they directly enter the bloodstream, and if it is say muscular, the drugs, then again they pass through the muscles and ultimately they pass through these capillary walls and go to their targeted area where they are supposed to work. So, this is how your drug distribution works inside the body. So, while doing this mathematical modeling, so we follow that this drug that is present in the system, they follow certain laws. And what are the laws? So, in this particular case, so when the drug enters into your body, obviously it will decrease and till it passes, till it find the targeted region, and that is proportional to the amount present in the body. So, this is one assumption. There can be more assumption. It can be say it is proportional to the square of the amount that is present to the body and so on. So, in this particular problem, if we take that the rate of decrease is directly proportional to the amount present in the body. So, the rate of decrease is ddt of Ct, where this Ct is the concentration of the drug. So, they is proportional to the amount present, which is again Ct, and this k is the proportionality constant. And since it is decreasing, we have a negative sign. And let us assume that the initial drug that was given to the body is some concentration d at time t equal to 0. So, we have dc dt is equal to minus k times c, and we have our C0 is equal to some t. So, simple differential equation, we just differentiate them, integrate them by separating the variables, and we get here ln c is equal to some kt plus some constant. Say I put it as log a. So, I get log ln c minus ln a is equal to minus kt. So, ln c by a is equal to minus kt, which implies c by a is equal to e to the power minus kt, and ultimately Ct equal to a e to the power minus kt. Now, the initial condition says that at time t equal to 0, the value is capital D. So, I put C0 equal to a e to the power 0 is 1, and this value is t. So, the value of the constant is d. So, Ct is equal to d e to the power minus kt. So, this is the concentration behavior of the concentration of the drug at any time t. Now, let us see that sometimes it is required to give some doses of the drug. So, let us assume say at time t equal to capital T, an equal dose, say the same dose D of the drug or medicine is added. So, what happens is that at time t equal to t, capital T, you already have d e to the power minus k t, because your concentration is C t equal to d e to the power minus k t. So, if I want what is the drug at time t equal to capital T, this will be C t equal to d e to the power minus k t. So, at the time t equal to capital T, another dose of drug is added, which is an equal dose T. So, this is the concentration of the drug from the previous dose, and then you add another dose T. So, at time t equal to capital T, this is the amount of drug now present in your body. So, if you want to find what is happening after you have pushed another drug inside the body, then your initial condition changed. So, your equation was C t equal to some A e to the power minus k t. You use the initial condition that C 0 is equal to D. But now you have to use the initial condition, what is C t, that at time t equal to t, your C t is D plus D e to the power minus k t. And if you do that, then this is going to give that C t is equal to A e to the power minus k t, and that value is equal to D plus D e to the power minus k t. So, from here I get the value of A, a new A, which is equal to D e to the power k t plus t. So, this new A will now be substituted here. C t is equal to D plus D e to the power k t into e to the power minus k t. Now, as your t goes to 2t, then what will happen here? This concentration. So, you have this interval, first it is at time t equal to 0, then at time t equal to t, now time t equal to 2t, and so on. So, at time t equal to 0, you saw that your concentration, you start with some d, and here also another plus d is pushed, here also plus d is pushed. Now, from here to here, the behavior follows this particular law. But then again, from here to here, since another plus d has been added, now it follows this. So, as your t now approaching this 2t, your C 2t will approach to d plus d e to the power k t into e to the power minus t is replaced by 2t. So, 2 k t. So, once it reaches this 2t, so the concentration of the medicine, of the drug at time t equal to 2t. So, there it will be d plus d e to the power k t. This is multiplied by e to the power minus 2 k t, and another dose is added d. This is coming from this particular equation, which says that as t tends to 2t, your concentration tends to this particular value. So, at exactly at the time 2t, this is the drug which is present there, plus another d is added to it, and hence you get this particular thing plus a d, and this is your new initial condition, and the process goes on. So, if I continue this, then concentration of the medicine or the drug after time t equal to NT. So, as you can see from here, if I multiply this, this is going to be d plus d to the power e to the power minus 2kt plus d into e to the power minus kt. So, I can take this d common and it is 1 plus e to the power minus kt plus e to the power minus 2 kt. So, this can be simplified to this. This is for t equal to 2t. So, the concentration of the drug after time t equal to nt can be written as d into 1 plus e to the power minus kt plus e to the power minus 2k times capital T and plus e to the power minus nk times capital T. So, if it is t equal to 2t, here it is minus k times 2t. So, if it is t equal to nt, it is minus n times kt. And this comes in a GP series. So, if I want to find the sum with common ratio e to the power minus kt, so 1 minus e to the power minus n plus 1 kt divided by 1 minus e to the power minus kt. So, this is the concentration of drug after time t equal to nt. And as your n becomes large, your CNT will tend to a steady value that this part goes to 0. So, it is d by 1 minus e to the power minus kt. Let us now see the numerical solution of this particular model, for which I will be using this Microsoft Excel. So, as you can see that I already have this equation dc dt equal to minus kc. The initial drug is d. The numerical value I have chosen d to be some 50, this k equal to some 0.2 and h equal to some 1. And we will be using this equation. This is the Euler's equation to solve this differential equation. Already I have done it, but to show you again, this is say t and this is ct. Let me increase the font size 20, make it a bit bold and in the middle. So, let me plot about say 40 points. Okay, so first this is 0 and this value is 0 plus 1, and then I just drag to the next 40 points and up to 40. Next we calculate this, sorry, this value is 50 as mentioned here. So, I will calculate this is equal to, so this is the initial concentration of the drug and this is equal to C0 plus H, which is a constant. So, I put a dollar sign multiplied by minus Kc. So, minus K is 0.2, again it is a constant, multiplied by C, that is the initial value. I close it and enter. So, this I drag till the next 40 values and I get the values. Now, I want to plot it. So, I highlight this. I go to insert, I go to this scattered diagram and I choose this. So, if I click this plus sign, so I see I do not want the grid lines, I want the axis, I want axis title, and if you want you can have the legend. So, if I want to change the chart title, I click here and you just say drug distribution in a body. This is your time. This is the concentration of the drugs. Oops. Concentration. And if you want to change this, the title here, the series 1, if you want, you go to this drug design, you select data, and here is your series 1, you click edit and you just write concentration and you click OK and OK. So, you see that here the concentration has come. So, this is how you generate the figure. So, I do that again and again so that you just get accustomed to it, that how to get the numerical solution of a particular problem. So, we come back to our original problem. So, now you saw that our solution is going to be in this type, that you start from some initial value which is 50 and then you go like this. So, I think I have the curve here like this. So, you start with the initial value which is 50 and then your drug concentration ultimately goes down to 0 at some point here. And these are the initial conditions which you have used. So, with this we come to a particular problem where the drug concentration is directly proportional to the amount of drug present in the body. If you want to vary the problem, you can say that okay, I can take dt dc equal to minus some k times square of the drug. You can keep your initial dose as d, or you can again change the law by saying okay, let me put a bit more complicated, e to the power c, where you keep the same concentration. So, that is how by changing the law you can give a different kind of solution, and but the curve will the dynamics of the curve will remain the same, because it will start with certain value and slowly the drug is used up inside your body. So, this is going to decline and come to 0. Now, the declination may be like this or declination can be like this, whether depending on the law which you are choosing, so that the concentration comes down at a slower rate or sometimes at the higher rate. So, clearly when this is exponential, it is going to come down at a higher rate. We now look into the numerical solution of these models, and let us check whether what I have just told, whether it matches with the solution. So, the first equation is dc dt equal to minus kc square and C0 is equal to D. So, our initial condition is 50, K is 0.01 and H is 1. So, I have my time T and my concentration as Ct. So, I change the fonts to be 20, center them, make a bit bold, and let's make the font size same as 20 and center them. So, the first thing is this value is 0, the next value is 0 plus 1, and let me drag this to the next 40 values. This is equal to, we will use the Euler's method. This initial value is 50 and this is equal to your C0 plus H, which is a constant. So, I put a dollar sign and this is multiplied by, I open a bracket, minus KC0 square. So, minus then K, which is again a constant, multiplied by, this is C0 square, bracket closed and end. And let me drag this so if I now plot this, I will choose these two. Using the cursor, I go down up to 40 values and I click insert, I choose the charts and I take this smooth diagram. So, name of the chart, drug distribution, I remove the grid lines, I want axis title and this will be time and this will be the concentration of the drug. So, this is the figure which is the graph which you get from the equation dc dt equal to minus kc square, where the law has changed from minus kc to minus kc square. Let us now look into the other equation where you have dc dt equal to minus k times e to the power c. The initial concentration is d, that is 50. However, the value of k we have taken very small, otherwise this, because of the function e to the power c, the concentration reaches 0 very fast. So, that is why such a small k we have taken. So, again we have this c, the time, the concentration, we increase their font size, make it bold, and this is 0 and this is 50. Just quickly make them 20. That's so this first we increase them by 1 plus 1 and then drag them to the 40 values, and this is equal to, again we use the Euler's formula for solving this first order differential equation. So this is equal to C0 plus H, which is a constant, multiplied by minus K. It's quite a small value, but again a constant, multiplied by e to the power c. So exponential c, which is C0 in this case. This is closed, again closed by another bracket, because this exponential is in this first bracket and then this bracket has to be closed by the last bracket, and I get the value. So sometimes if it is coming in exponential, you can just go to the number and either 2 or 3 or 4 decimal places. So that will give you in terms of decimal values. Now you have to plot this to see the dynamics. So I choose the 40 T and the concentration values, go to insert, go to chart and then click. So this is the graph. I format them in a little, say drug distribution. Let's see what is I name, drug distribution, same, and I choose this. I remove the grid lines, I choose the axis title, and this is the time, and this is the concentration of the drug. Okay, so you can see there is a sharp fall and then it's going to some steady value. So let's go back to the slides again and compare. So as you can see that here we have 3 graphs. This one is dc dt equal to minus k times c. We have kept the same concentration C0 equal to D, and the value of K also same here, it is 0.01. So if you see this particular diagram, the plots with the law minus Kc, you can see that it starts with the concentration 50 and gradually goes down to 0. Then we come to this law, which is now minus Kc square. We have the same initial condition 50, the value of k is 0.01, and then it starts from 50, but because it is minus k c square, you can see that this decline is sharp one than this decline. So, with this minus k c square, the concentration of the drug will be used up rapidly with a sharp decline, and then it is going to some steady value. When it is e to the power c, here the decline is much sharper, straight down. However, the value of k has to be extremely small here, because otherwise this will just goes to 0 in just 4-5 steps. The concentration of the drug is kept as 50. So, a sharp decline, and then it is going to some steady state value. So, as we have told before, that the concentration of the drug, its dynamics will depend on what kind of law you are choosing, and depending on a particular drug, we choose a suitable law. So, in our next lecture, I will be taking up some growth and decay model of the electric circuit, and till then, bye bye.